But fortunately in 102, yeah, all of y'all are in 102, we're going to do sound this semester too, which we've never done sound before, but it's a pretty important chapter. It comes up a lot. In fact, I was talking to a student who took the MCAT just recently, Ainsley. I don't know Ainsley Pratt, but she there was just one physics question she said on the test, and it was about sound, and it seems to pop up a lot on the practice test too. MCAT's different every time, so like you could have one question this time, and then next time it's like you get a whole bunch of physics. So the MCAT changes every time you take it. All right. When are y'all taking it? Does anybody know? You should be trying to take it this summer. Yeah. Oh, cats. All right. But anyway, some of the stuff you've seen, some of it we're going to see in a little more detail or a little less detail in the 102 class. And also, we're going to do nuclear physics next week. I sent an email out earlier. I think that's chapter 9, if I'm not mistaken. Yeah, atomic and nuclear phenomena. And we're not going to cover that at all in 102. So you'll want to give that chapter a good read, because we won't cover it at all. You probably haven't seen a lot of it. You might have seen some of it in the in your chemistry class, but a lot of it you've probably never seen before. Bless you, Kat. All right. So the first part of this is just sort of some basic stuff about waves. Now you have transverse waves versus longitudinal waves. We describe these exactly the same way with frequency and wavelength and all that jazz, but I like to think of it as the transverse and the longitudinal waves. The transverse would be like the wave, and so like as I step in front of your row, you raise your hands up. Y'all know like the wave at the stadium? And so like that would be a transverse wave. You're the medium, and the medium moves up and down, up and down. So that's a transverse wave. But a longitudinal wave is a little bit different. So when I stand here, you like hug the person next to you. You don't really have to hug. But imagine that when I'm here, you hug, and then you go apart, and then you hug, then you go apart, and then y'all hug. You can hug if you want. You don't have to. And then you go apart, and then you hug. So instead of the medium going up and down, the medium goes side to side. Okay, that's transverse versus longitudinal. Sometimes longitudinal is called a compressional wave. And we'll deal with both of these. Transverse waves, we treat light like a transverse wave. It's a little more complicated than that, but not much more. It's a transverse wave where the medium goes up and down. And longitudinal waves very much are sound waves. Sound waves have pressures, they have compressions and rarefactions in the medium, the atmosphere, the sound, or whatever. Transverse waves, again, up and down, like a wave at your stadium. Longitudinal, side to side. It's like the hug wave, I think of. The hug wave. Let me get the microphone. You ever watch Seinfeld? Don't even talk about? Yeah. Okay. I'm a low talker. You remember the low talker from Seinfeld? No, you've never watched Seinfeld. Anyway, so longitudinal versus transverse. All right. Longitudinal versus transverse. We have some things to describe these different waves. They have a wave speed. We'll call this V. We have a period. The period is the time for one oscillation. I'll draw it for you in just a second. That is T. And then you also have the frequency. This is the number of crests that pass in a given time. It's the inverse of the period. So the frequency is 1 over the period. If we were to look at a wave, say a transverse wave like this, if we're looking along the x-axis, we're looking at time, and along the y-axis, we're looking at displacement. So like you'd have your transverse waves going up and down as a function of time. Then my period would be the time for one complete oscillation. So the period would go from this point over to this point. So this distance, or this time rather, would be one period. And then my frequency is just going to be the inverse of that. With frequency, you've probably seen this before, but let's say I have two waves like this. I have one like that, and then I have one like this. Which one of these has the longer period? Has the bigger period? The top or the bottom one? The top one has a longer period. The period is from this time all the way over to this time for one complete oscillation. Be careful that you don't do from here to here. It goes from here all the way over to here because that's one complete oscillation. I'm on the up part, and I come back here and I'm at the same position on the wave, where the wave begins to repeat. So that wave begins to repeat at that point. Which one of these, the top or the bottom, has the higher frequency? Remember, the frequency is the one over the period. So which is it? The bottom one has a higher frequency. It's like it's more rapid. We'll talk about that in terms of sound in just a bit. Your book also talks about angular frequency. We're not really going to get into that, but it is a pretty important concept. Angular frequency is related to our frequency, and it's omega 2 pi f. I always think about this in terms of units. Omega is in radians per second. This is radians. There are 2 pi radians in a circle, and then this is 1 over seconds. So that's our angular frequency, and it's related to our frequency. We can plot our waves in two different ways. So the plot that I showed you before shows the wave through time, but I can also make a plot of my wave in x and y motion. So this is the y displacement, and then this is the x displacement. This is a different graph. It looks like the same graph as what I had before, but it is a different graph. It doesn't show the wave in time as time progresses. It instead shows the wave as a snapshot. So here we can show a couple of other things about this wave. One is the wavelength. The wavelength is the distance from this point to this point. So this distance is one wavelength. Now, be careful, don't get this confused with period. Period and wavelength are similar. In fact, a wave travels one wavelength in one period, because a wavelength is a complete oscillation. All right? But they're different because this is a different kind of graph. This is not time on the x-axis. Instead, this is x displacement on the x-axis. All right? If you're not getting this, we're going to see it again in the class later in 102. And all of you are in the class? Oh, Malcolm, you're not. Yes, in 102. Okay, so you'll see wavelength and period and all that jazz later. You can have waves, and it talks about phase. You can have waves that are in or out of phase. And we'll see this in chapter 7 or 8, chapter 8, next chapter in 102. So if I have two waves, I'm going to show you a wave here. I have a wave that looks like this, and then let's say I have another wave that looks like this. Now these waves have different amplitudes. The amplitude, by the way, I didn't say this, but the amplitude is the distance of the highest peak. This is the amplitude. We usually call the top parts of these crest, like the crest of a wave, and we call these troughs. You can have waves that add up, like for example these two waves. We would say that these waves are in phase. What that means is that peaks line up with peaks, or crests line up with crests, and troughs line up with troughs. So crest line up with the crest here, and then the troughs line up with the troughs. So this is an in-phase wave. In order to be completely in phase like that, you have to have the same wavelength. Now, you can also have waves that are out of phase. this wave is going to be 180 degrees out of phase. And when I have a wave that's 180 degrees out of phase, it's going to have the peaks will line up with the troughs. So these waves will look like this. These two waves are out of phase because my peaks line up with my troughs. Now, when you add up waves like this, if I add up these two waves, if I combine them, what I get is nothing at all. Because when the peaks, which have a positive value in the amplitude, line up with the troughs, which have a negative value, they work to cancel one another out. You see this, you've seen this before, like out on boats. When you have two boats that come together, the waves, when they come together, you'll see really deep troughs in them, or you'll see really bigger waves. Often you see it as when you get two in-phase waves, they produce bigger waves. And what's happening there is when you add up two in-phase waves, remember in-phase waves look like this. When I add up two waves like this, I get a wave that results that has a much bigger amplitude. All right, so if I add two waves together that are in phase, when their peaks line up with their peaks and their troughs with their troughs, then it causes a larger amplitude. This previous example, oh shoot. With our waves that are out of phase, this is called destructive interference. In your book, they talk about how this principle, interference. Hey, we've learned a new word at home. You want to know what it is? It's a cool word. Indubitable. You know what that word means? My kid's got a little pen. When you press on the pen, it says indubitably. Indubitably. It means like for certain or for sure. So if somebody asks you the question like, hey, you going to go have lunch now? You can say, indubitably. Anyway, destructive interference. Destructive interference occurs when you have these peaks line up with the troughs. And in your book, it talks about how noise-canceling headphones. Y'all have a set of those at home? Maybe you do, maybe not. But what those do is they take the waveform that's coming in, or they have microphones on the outside, and they sort of pick up all the ambient noise. And let's say that ambient noise function might look like this, some sort of crazy thing, and then it produces another sound that's the inverse of this sound. So it will produce a sound that looks like that, and when you add them up together, you get something that's a little bit of noise, but nothing like what you had before. That's how your noise-canceling headphones work. In fact, if you have a speaker, I don't have one of these, I want to get one. But if you have a stereo at home where you can actually unplug the wires off the back, they have like the little red and black things. Do y'all have any of those? No, you don't really make them anymore. But you can switch the wires on one of the speakers and then put the speakers right up next to one another. By switching the wires, you invert the signal, kind of like on this black and blue with the noise-canceling headphones. And when you put the two speakers together, instead of getting louder, the noise goes away. Isn't that bizarre? I just read about this in a magazine. But I don't have a stereo to do that. But if you have one, try it, because they say it works. All right. So anyway, those are our different kinds of interference, destructive and constructive interference. We're going to do this in Chapter 8, so we'll see this all again for the 102 class. Let's do a few little questions. I brought you some problems. We don't have a whole lot of time today. Yeah?
So, in-phase waves cause a high amplitude.
I'm sorry, what now?
In-phase waves cause a high amplitude.
When you get two waves that are in phase and they combine together, yeah, you get a bigger amplitude.
And so, if they're not in phase, does it result in a low amplitude?
Does it what now?
If they're not in phase, does it result in a low amplitude?
If they are completely out of phase, then they get an amplitude that goes away completely. If they're not completely out of phase, I don't know how important this is. It's sort of important. Like, let's say that I have a wave that looks like this, and then I have a wave that's just, slightly out of phase. Like that. then you might get something that instead of going to a straight line where it all completely goes away, you'll get something that's a little more complicated. You might get something that's has a smaller frequency, or it even has like more wiggles in it. As you mix more and more frequencies together, then you'll get these more complex sounds. And in fact, our voice and music, those are many different frequencies of sounds coming together, and so they have a very complicated function. It doesn't look like this at all. Can I show you all something? This isn't really in the book, but it's kind of cool. It's a little bit related. In fact, if we have a chance, we'll look at some questions from my handout. Tone generator. Yeah, this is a good one. So, first of all, do you know what the range of human hearing is for frequency? Do I know? It goes down to about 20 hertz up to about 20,000 hertz. So that gets worse as you get older. Typically your high frequency. This is 440. That's not that annoying, right? Now let's go up. Y'all can hear that? Can you hear that? See, nothing. Anybody not hear it? How about this? Can you hear it? No. This? Who can hear it? Raise your hand. Still? I'm going to turn it up because nobody else can hear it. Tell me if this is too annoying.
Oh, okay, yeah.
Okay. I'm sorry. I can't hear it at all.
Really?
Yeah.
Oh, I know that's kind of the same thing for dogs.
Right.
Like that one's where it like shuts them up.
Right. So a dog whistle is very high frequency. It's even, I think it's like 30 or 40,000 hertz because they have a much higher range in their audible spectrum. This is the low frequency. You really need some of those really big speakers that go boom, boom, boom to do this, to make it work, but that's 40 hertz. Y'all can hear that, right? Yeah, let me turn it up a little bit. Y'all hear that? Let me turn it up. You might be able to not hear it, but sort of feel it.
Yeah.
Sort of sense its presence a little bit. That still? Yeah, it sort of goes away. Anyway, that's the range of hearing. Now, let's imagine that I have two tones together. This is really what I want to show you. What do you want? That's sort of not annoying, right?
Yeah.
So 147, and now I'm going to make another tone that's very similar, but a little bit different. Wait, 147. Turn this one back on. So now we have two waves have the same frequency. When I start to combine them, you start to create more complicated waveforms. And those are actually called, you heard the wah, 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 wah. Do you like play guitar or any kind of musical instrument? Play guitar. So you know how to tune a guitar? Where you hold one string on one note and the next string on the same note, and you listen for that wah, 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 wah. And then with your ear, you can tune them until they come to the same frequency. It's very effective because you can get it within a hertz or less, even very close just with the human ear. Those are called beats. We might come to that in a little bit.
So does that mean all people have a hard time tuning guitars?
No, you can hear a beat pretty easily. I mean, you can hear that, right, when I did it? Because you're not looking for frequencies, you're looking for that wah, 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 wah. And notice there's a difference in frequency of 2 hertz, and that's actually the frequency of this tone. 1, 2, 1, 2, 1, 2. It's 2 every second. I'm going to go to my office. I'll be right back. Okay. Anyway, let's do some of these questions. Where are they? Oh, there.
Are you looking?
Yeah. Let me pull it up right quick. And we might actually bring this chapter into Friday, so let's just plan on that. Whatever we don't finish today, we'll push it on into Friday. And then if we get a chance to do nuclear, to start nuclear on Friday, we will. But otherwise, we'll just continue with that on Monday, because both of these topics you're not going to see much at all in the class, so except for this one this semester, so that's good. Okay. Okay, let's do these first questions. Number 646. You have this little wave here. Now remember, we wanted to find the wavelength. Now this is not like what I've shown you before. Like, this is a funky function. So I want to know, what is the approximate wavelength of this? It shows you the y displacement versus the x displacement. Remember, the wavelength is where the wave begins to repeat itself. So you want to ask yourself, where does this wave begin to repeat itself? And what is that distance? The distance for one complete oscillation. If you finish that one, go on and do 647. And then also 648. All right, just a few more seconds. I'll stop at 1 minute. Well, not many of you have it. I'm going to stop at 1 minute. Okay, is anybody really confident in their answer? Who's confident? It's not A. Anybody confident? Okay, the answer is C. Is that what you're going to say? It is C. It's 4 meters. Because if you notice, watch, it repeats itself. Like, you got this little feature right here, you get that same feature right here. It goes from here to here. So this whole function right here is the wavelength. It's the time for one complete oscillation, and we get one oscillation in 4 meters. Let's try 647, the second one. The speed of the wave is 2 meters per second. What is its frequency then? No, it's wavelength. How are wavelength, speed, and frequency all related? All right, stop at 50 seconds, say. Okay, good. B is right, I think. Yep, B is right. So remember, our speed is equal to our wavelength times our frequency. I'm not sure, did I say that earlier? Okay, y'all just knew it? Because y'all are smart like that? All right, it's in your book, of course. It's in your book. Okay, so the wavelength, we're looking for the speed. Our 2 is our speed. The wavelength we've said is 4, so that means the frequency has to be a half a hertz, or a half of an inverse second. Let's try 648. If the frequency is 2 hertz, and the wave is propagating to the right, how long will it take it to pass the 5 meter mark? At point A. How long will it take point A to pass the 5 meter mark? All right, I'll stop at 105, 105. Okay, so if the frequency is 2 hertz, we know the wavelength is 4 meters. The frequency is 2 hertz, so that means the speed is 2 times 4, or 8 meters per second. And I want this point to go over here, or excuse me, not there, to the 5 meter point. So I want point A to travel this distance. What is that distance? That's 4 meters. So I'm traveling a distance equal to 4 meters. At 8 meters per second, that's going to take me a half a second. So 0.5 seconds is the right answer, A. What's the amplitude of the wave? Just reading it off the graph. When we finish this one going on, look at 680. It's the one with these wavelengths right here. This question. All right, I'll stop at 30. I'll just go to 28. See, right? Yeah, that looks right. So our amplitude is just our maximum displacement. Our maximum displacement is right here, which is 1.5 centimeters. Or you could measure it right here. That's also 1.5 centimeters. That's the maximum displacement. Now let's look at number 680. Which pair of these waves is in phase? X, Y, or Z, or both X and Y? Which is in phase? I'll stop at 18. 20. Missing somebody out there. All right. Okay, good. A is right. Those are in phase. Remember, if they add up, we're going to have destructive or constructive interference. We have constructive interference. So we'll get a bigger amplitude there. What about 681? Which ones experience only destructive interference? X, Y, Z, or both Y and Z? I'll stop at 20. Awesome, B is right. Destructive interference. If I add these up, it goes away. Actually, it's not going to go completely away because the dashed line is not the same amplitude. So I will have a little bit of a residual, but it's just going to be very tiny. It's going to look sort of like this when I subtract those two waves from one another. And then which pair will experience only constructive? We've already said this, but 682 right here. I'll stop at 15. Awesome. A is right. That's constructive interference, or total constructive interference. Z, by the way, experiences both constructive and destructive. So parts of it cancel out and parts of it add up. You have these in betweens. We'll talk about that in 1 or 2 in the next chapter. Let's look at standing and traveling waves. So if you have a traveling wave, that means that the wave just continues to travel down a string. Like say for example you have your hose and you do it like that, or a rope or something, you do it like that, and the wave just travels down the rope or the medium or whatever it is. But you can also have standing waves. A standing wave occurs when you say close off one end of the wave and the wave actually reflects back off of the surface, and it will actually start to bounce back There's a picture of this in your book. The wave will bounce back. And when you get this, this is called a standing wave. A standing wave is like on a guitar. When you pluck the string on a guitar, you get this wave that moves back and forth, back and forth, back and forth. So in a sense, it's a traveling wave, but because it's constrained on either end, it begins to set up both a traveling wave and then a reflected wave, and we call that a standing wave. And they can interact with one another. The traveling wave, we have a couple of things. We call the point where these two cross, this is called a node, and this is called an antinode. Let's see. If you have a string, like on a guitar, what do you have at the end of your guitar string? So I have these waves. This is my guitar string. They're connected at either end. And then it will reflect back and bounce along the guitar string. The wave will reflect off the end, and you'll get this standing wave. At this point, at the ends of the string, what will you get? Nodes or antinodes? What do you think? An antinode is where you get one wave that's up and one wave that's down. A node is where you get two waves that are at zero displacement. At the end of the string, because it's not allowed to vibrate at the end, you're going to get a what? You're going to get a node at the end. So if you have a guitar string, for example, you'll have a wave that looks like this, a standing wave, and at the end you have nodes here and here. However, you can also have, and we'll see this in a little bit with resonance, you can't have this with a guitar string, but you can have it with a musical instrument where you have one end that's closed and one end that's open. And in this case, you're going to have a node here, and then at the other end, you'll have an antinode. So you have a node at the closed end. It's like the wave gets stuck there. When it hits this end surface, it can't, you can think of it kind of like the guitar string, that it can't oscillate back and forth at this end. But down here, it's like it's free to oscillate back and forth. If that helps you think about it. But when you have an open tube like this, you get a node at one end and an antinode at another end. So that would be like this. This is a tube that is closed on one end and open on another end. And let me get the thing out. We'll talk about the resonance and how it works. But I get a node on this end and an antinode on this end. All right? With a closed tube. Or excuse me, with a tube that's closed on one end but open on the other end. So anytime you have an open end on a tube, that's going to be an antinode. If it's closed on one end, that's a node. That might seem trivial, but it'll become important when we get into standing waves. Okay. Resonance was really, the section on resonance was really just sort of some vocabulary stuff. You can just read through that on your own. If you would, read through that section, page 228 and 229, about resonance. I don't think that you'll see that kind of thing on there when you have forced resonance, when you're actually forcing something to oscillate. So we're just going to skip over that. But let's begin looking at sound, and we'll come back to the tube here later. So sound, when we're talking about the speed of sound, it's dependent upon a couple of things. It's dependent upon the bulk modulus and the density. And that speed is given as b, the square root of b over rho. B is the bulk modulus. Sometimes we also call this elasticity. I don't think your book calls it that. But the bulk modulus describes, if I take a molecule in this substance and I displace it a little bit, how much does it want to go back to where it is? And if it wants to go back a lot, then it has a really high bulk modulus. If it wants to go back just not very much, it has a really low bulk modulus. So what do you think has a higher bulk modulus? A gas or a piece of metal, for example? Which one of those has a higher value for beta, this bulk modulus? The gas or the metal? The metal, right. Because if I displace a molecule or an atom within that metal, then it really much wants to go back to its original location. You understand what I mean by that? It has a high bulk modulus. So this value for beta, what's a beta? Actually, it's capital beta. It's increasing when you go from gas, liquid to solid. As they get more solid, those materials have a higher bulk modulus. So beta increases when you go from gas to liquid to solid. And so as a result, what does sound travel faster in? Gas, liquid, or solid? It travels a lot faster. Like in air, the speed of its sound is something like a few hundred meters per second. If you have a steel rod, it's something like 15,000 meters per second. It's a lot faster in a solid. And in fact, it's faster in water. If you ever try to talk to somebody underwater, make noises, that sound travels a lot faster in water than it does in a gas.
But you can't understand.
But yeah, that's beside the point. Right. Okay, so the bulk modulus, this increases from gas to liquid to solid, and as a result, the speed of sound increases as well. In the same way, from going from gas to liquid to solid. All right, this is our density. So as our density increases, the speed of sound decreases. All right, as this goes up, this goes up. As this goes up, this goes down. It's not a direct relationship, it's an inverse root relationship, I guess you'd call that. Excuse me. Okay. Just real quickly, pitch, and then I'll let you go. 6:15 we get out, right? Or is it 6:45? This class really should end at 6:05 because it's only supposed to be an hour and 20 minutes long, but somebody put it at an hour and a half for some reason. I'm sorry I just told you all that. I shouldn't have told you that, should I? Okay, just a couple more minutes. I know you're tired, so am I. So frequency, pitch. A couple things about sound. Pitch is related to frequency. So if you have a high frequency, you have a high pitch. If you have a low frequency, you have a low pitch. Hey, y'all try this out. High, low, high, low. Can y'all do that? See, it's not easy, is it? I've practiced for many years to do that. I amaze my children. They can't do it at all. All right, so anyway, pitch is frequency. Amplitude is loudness. I think that's all. Yeah. And we'll stop there, okay. We'll pick back up with sound. So go ahead and read chapter 7. We still have quite a bit. We might not get to nuclear stuff at all on Friday, but we will cover the nuclear chapter. That's very important that you see that. Okay, folks? I'll have your girls posted and sort of an overall standing of where you are in the class tomorrow. Have a great night. I'll see you on Friday. I'm with you for a few days. I think I'm with you through Monday. I forget. The schedule is updated on the web.